Well, good morning. It's 11:40. I'm 10 minutes late getting started. Sorry about that, but I had several things that interrupted. Now, I guess you don't really care, but anyway, just have gotten here. But I'm the only one in the room right now. I know Josh, I know had a funeral last week. I don't know if you're back from that yet. And then Dawson told me yesterday that he wouldn't be here today, so I guess I'll be in here all by myself unless Josh comes in. And also, Dawson was going to record how far we got in our matrix on page 31 in section 1.3, example 7. And since he's not here, I can't get that from him, so we'll just have to leave it, and if he brings that next time, then we'll go back and figure that out. I don't think it's worthwhile for me to try to recreate that because I don't have it. I'd have to go back to the YouTube video, and that would take so much time to do that. So if you have any questions on example 7, we'll finish that when you come next time. Okay, that did finish 1.3, and I think I've already given you all the homework exercises there. But in case I haven't, any of the odds 1 through 11, they're all at calcchat.com. They're also in the back of the book, but both those places you can look. 13's at CalcChat, 15's at CalcChat, 17, okay, I'm sorry. The first 1 through 11 are polynomial curve fitting. You don't have to do that unless you just want to. We just sort of scooted by that one. Same thing for 13 and 15, but they are at CalcChat. The 17 and 19 are just sort of following up with the same type of thing, so you don't have to do those unless you just really have a hankering to. But the network analysis at 21, you can do either 21 or 23, are both regular networks, not necessarily electrical networks. 25 and 27 are electrical networks, like we were doing in the last examples that we did. And then 29 is a temperature gradient type deal, so you can give that a shot if you would like. We haven't done the partial fraction decomposition, which I'm having trouble seeing. I know it was in here somewhere. Or maybe it's just there. I was thinking they did at least one in the book text with it, but I don't see it. But if you have done your partial fractions in calculus, which I know you have done, then you have probably done some of those, so those are there as well. And then calculus, there's a problem there. It's an eigenvalue problem. I'm pretty sure that one is. And there's some others. So you can do any of those you want, but the ones we focused on were your network. Now, I've given, I know I've given at least Dawson, and I think maybe Josh too, but if not, Josh, you can come get it. Well, here comes somebody. Oh, can I help you? Okay, I'm recording a class. It goes until 12:45. What do you need? I'm sorry? I can't hear you. Oh, you're going to miss class? You mean the physical science?
No, 1:30 113.
Oh, you missed 113. Okay. Do you need your test? Okay, let me pause this.
And don't collapse.
I'm sorry? All right, sorry about that. I had a student who missed class this morning. I gave out the first take-home test, so I had to stop and go get her the test. Well, I was just going to say, if you need more practice and you might find it helpful on the first test, there are some review exercises at the end of Chapter 1, beginning on page 35, and you can see CalcChat.com for worked out solutions to the odd number exercises. And by the way, in this new text, there is a QR code that I assume takes you to CalcChat.com. So if you have that on your phone that you can take, read the QR code, you can just do it straight from there. But you could do any of the odds 1 through 5, 7, 9 through 19, 21, 23 or 25, 27 or 29, any of the odds 31 to 39, 41 to 45, 47 or 49, any of the odds, well, I'd say 51 or 53. There's a writing exercise 55 that should be at CalcChat.com. And there's 57 should be at CalcChat.com. There's a true-false 59 should be at CalcChat.com, and then there's an application number 61 that should be at CalcChat.com. Then the fractional partial fraction decomposition, again, you can do those if you'd like. That's up to you. 63 is one of those. Polynomial curve fitting, if you'd like, that's 65. And then sales, I think, are polynomial curve fitting, 67, 69 would be two of those. 71's a network analysis, and 70, well, they don't, the only electrical network they give is 72, but those answers are in the back of the book. All right, but anyway, that finished Chapter 1, and you do have your test, or you should, on Chapter 1. Okay, if you don't, come see me and get your test. We're going to start Chapter 2, which is matrices, as if we have already been doing matrices. So we're going to do at least 2.1 through 2.4. We probably won't do Markov chains and more applications of matrix operations. I think that's a new section in this new book. I'll have to see what that one is, because I don't recall that from the previous edition. Maybe it was there, I just don't recall. So let's start with 2.1, operations with matrices. Now some of this, especially the early stuff, will seem very elementary, and it sort of is. And then toward the end of the section, we'll be talking about elementary matrices, which are not so elementary, but, well, in a sense they are. But anyway, let's start with equality of matrices, okay? And I think we've already hit some of this before, but in case we haven't, or you don't recall, or we didn't go into it in this kind of detail, let's hit it. First, when we're naming matrices, we usually name them with uppercase letters. Let me get my pen set up. Okay, A, B, C. That usually represents a matrix. Okay. A representative element would be A sub ij, B sub ij, or C sub ij. Okay? Now, catch the difference here. The elements are lowercase letters. usually given the same lowercase as the name of the matrix, capital A, capital B, capital C, and then the subscripts ij refer to I being the row number, J being the column number. So if you have a n by m or m by n matrix, I would go anywhere from 1 to m, and J would go anywhere from 1 to n. Okay? But that would be a representative element enclosed in brackets. This also describes the entire matrix. You know, these are equivalent expressions of the same three matrices here. Matrix A are the bracket Aij, where I would go from 1 to m. If A was the m by n matrix, J would go from 1 to n if that was a m by n matrix. Same thing with B and C. The third way you can do it is just write out all the elements. And again, you would put these, I'm only going to do this for A, I'm not going to do it for B and C. But that would be A11, A12, A13, dot, 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 A1, and let me make sure I'm giving you the same one, N, A21, A22, A23, dot, 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 up to A2N, A31, A32, A33, dot, 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 up to A3N, dot, 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 down to AM1, dot, 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 down to AM2, dot, 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 down to AM3, and then dot, 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 down to AMN. That would be your M by N matrix written out with all the elements in it. Okay? In this text, we're dealing primarily with real matrices. All the entries are real numbers. Okay? So, you can, of course, have complex matrices. We aren't going to be doing those. All ours are going to be real. Now, two matrices are equal when their corresponding entries are, every one of them are equal to each other. So if all three of those matrices we did up there were M by N matrices, they would be equal if and only if for every ij combination Aij was equal to Bij. So the third representation there, the A11 would be equal to B11, and A12 would be equal to B12. Every one of them has to be identically equal. They have to be the same size, of course, and they have to have every element the same. So here's the way to express it. I think I'll go to a clean slide here. It's basically what I just said, but let me write it down since they have it in the book. Two matrices, A, which I'm going to do both forms, Aij, and B, which would be Bij, and the I's and the J's are the same size. These are equal. Two matrices are equal when they have the same size. That is absolutely necessary. When they have the same size let's call it M by N. That's what we've been using. Okay? And Aij is equal to Bij for all 1 less than or equal to I less than or equal to M, and 1 less than or equal to J less than or equal to N. So every possible combination, every element in matrix A, the corresponding element in matrix B has to be identically the same. or at least the same value. Like if one was 3 and the other was 9/3, those are the same values. So let's do example 1. Here are 4 matrices. A, 1, 2, 3, 4, very creative matrix. B, 1, 3. Now, written that way, we sometimes call that a column matrix or a column vector. Both of those would be fine. Naming it B indicates it's going to be a matrix. However, you could have called it a column vector as well, because it only has one dimension. Here's C, which is 1, 3. Oops. I sometimes tend to put commas where I shouldn't put commas. That time I did for some reason. 1, 3. Now that's not equal to B. Even though they have the same two numbers in them, they're number 1, they're different sizes. B is a 2 by 1 and C is a 1 by 2. Not the same size. And so the elements are out of place. Now C, you could call it a matrix, and it is. You could call it a row matrix, and that it is. Or you could call it a row vector, and normally we wouldn't use that nomenclature in this case. And here's a 4th vector, D. And D is 1, 2, x 4. Okay? Now, B and C, like I said, are not equal. And of course, neither one of them are equal to A, because they're completely different sizes. However, A and D are the same size, and 3 of the 4 elements are the same. They are equal if and only if x represents the number 3, or some other form of 3. Like I said before, 9/3 or 36/12 or something like that. That is very obvious that the value, whatever it is exactly 3. Okay? So matrix A and B are not equal because they're different sizes. B and C are not equal because even though they have the same 2 elements, they're in different order, so they're not the same sizes. A and D are equal if and only if x equals 3, or some other representation of 3. Now, as I said before, column B, the matrix B there is often called a column matrix or a column vector. Both of them are fine. And a matrix has only one row, such as C is a row matrix or a row vector. Okay? Boldface letters often designate column matrices and row matrices. So the other thing you can do, and this is what I was just looking at, you can partition a matrix. Like this matrix A can be partitioned to be the column vector or column matrix 1, 3, and the column matrix 2, 4. Now they don't usually write it like this, but I'm not going to put a comma there. This is a little bizarre, but you could put just a straight line there. And that's what they do with the representation that I'll get to in just a minute. This would be A1, and that's a boldface lowercase. That represents a vector. Now, they don't call it that. They say a column matrix, but a column matrix is the same as a column vector, and this would be A2. Okay? So then you could say that matrix A is the matrix made up of 1, 3, partition 2, 4, which you could say is A1 partition with B1. No, I'm sorry, A2. I was thinking back home. A1, A2. Since those technically are vectors, and they bolded them in the book, I'm going to write them with arrows over them. Now, so there's the first property, you might say, or operation that matrices do. Well, it's property, equality, okay? So let's look at some more addition, subtraction, and scalar multiplication. Notice I almost said multiplication of two matrices. That's coming later. This is scalar multiplication of two. So let me clear this out of the way, and we're going to add two matrices. The only way two matrices you can add if they're identically the same size. You cannot add a 2 by 3 to a 3 by 2. You just can't do it. Or a 2 by 3 by 7 by 5. You can't do that either. You have to have identically the same size, and then you can add them. So, and you add by adding the corresponding entries. Those that are the same. So here's your definition of matrix addition. If matrix A is this matrix Aij, and matrix B is Bij, okay? If these are matrices of the same size, my writing is pretty pathetic, and we'll go and name it M by N, their favorite size, okay? Then their sum and we'll call that A plus B. Wait, I'm going to write it the way that they did. Is also an M by N, because you don't expand any by adding. A plus B, and it'll have the same dimensions, and that will be Aij plus Bij. Okay. The sum of two matrices of different sizes is completely undefined. You can't do it. Okay. Now, I believe I'm going to take more room, so I'm going to erase this, and we'll do example 2. It's got 3 parts, so let's see how much we can get done. Here's the A part of example 2. Here's a matrix. Minus 1, 2, 0, 1. Plus, if we can do it, 1, 3, there you go, 1, 0. Goodness gracious, that came out ugly. Okay, came out really ugly. All right, if those are the two matrices, let me make sure I got them right. No, I erased the wrong one. Okay, let me make sure I got them right. Negative 1, 2, 0, 1. Add to that the matrix 1, 3, negative 1, 2. okay? 2 by 2 plus 2 by 2, yes, same size, so you can add, and you add the entries. -1 plus 1 is 0. 2 plus 3 is 5. 0 plus -1 is -1, and 1 plus 2 is 3. 0, 5, -1, 3. Okay. I rushed between classes and ate me a granola bar. I have a feeling I didn't drink enough water to chase that down because I was running out of time, and now my throat feels as dry as a granola bar, so sorry about this. I hope my voice is coming across okay. Here's the B one. Here's a vector. This one, a matrix. This one happens to be a 2 by 3 matrix. 0, 1, -2. 1, 2, 3. Okay, and they're adding to that matrix another matrix that is also 2 by 3, so you can add them. But this one happens to be that really bizarre little 2-for matrix. Okay, 2 by 3 matrix, but it happens to be all entries of 0, so we call that the 2 by 3 0 matrix. And when you add those, and then you add component by component or entry by entry, you get 0, 1, -2, 1, 2, 3. In other words, you do not change the value of your first matrix. That makes the 0 matrix, as long as it's an appropriate size 0 matrix to whatever matrix you're adding, in other words, same size as the one you're adding it to, it will always produce the same matrix because you're not adding anything to it. You're adding zeros, and that doesn't change the value. So we call the 0 matrix of the appropriate size the additive identity matrix. Okay? You add it to the other matrix, and it doesn't change values at all. All right. Here's another matrix, C. And this matrix is a column matrix or a column vector, 1, -3, -2. And we're going to add to that the matrix -1, 3, 2. -1, 3, 2, sorry. Can't get a spot to erase. Well, I guess we were just stuck with it. Okay. -1, 3, 2. Okay, now you add those together, and you can, because that's a 3 by 1 plus a 3 by 1. Both happen to be column matrices or column vectors. But since they're the same size, 3 by 1 and 3 by 1, you can add them, but when you add them element by element, entry by entry, that's a 0, that's a 0, and that's a 0. That produces the 0 vector of the appropriate size, 3 by 1. Now, what we call those two vectors, since they add to be the 0 vector, just like the number 7 added to the -7 in the real number system, coming out to we call them additive inverses of each other. That's the word I was trying to think of. Okay, one more addition. This is the D one. And here's what we've got. 2, 1, 0. 4, 0, negative 1. I'm going to add to that 0, 1, negative 1, 3. What do you reckon that gives us? Absolutely nothing, because this is undefined. Undefined because those do not have the same dimension. The first one's a 2 by 3, the next is a 2 by 2. You cannot add two matrices of different sizes, ever. All right, so that's your matrix addition. The top line on this page 41 says matrix addition, subtraction, and multiplication. We haven't touched on subtraction yet. We will get there, it's just not yet. We're going to do matrix addition we just did. We're going to jump to scalar multiplication. Then we'll do some subtraction at the bottom of the page 41. Sorry. I think because it's sort of a new subject, I'm going to erase this and come up with a the definition of scalar multiplication. But I think before I do need to get some water. Like I said, my throat is so dry. All right, sorry, I decided to go by my office since no students are here. I have no concept of the time except how much I've taught, but I've already had a couple of breaks when students have come in and stuff, so I wanted to make sure I didn't go too far over because I only have 30 minutes to eat lunch today, and I didn't want to go over. So I brought my phone up because I usually count on y'all keeping me up with time. So we're doing on in Chapter 2, matrices, 2.1, operations of matrices, we're going to define scalar multiplication, okay? Then we'll do subtraction and then combine sort of all these together, okay? So here's the definition of scalar. I'm sorry, even though I drank and tried to clear, I'm still clogging up badly, sorry. If matrix A is defined as this Aij, okay, and this is its standard M by N matrix, and C is a scalar. I'm sort of skipping some words here, but you can follow it in your book if you got it. Any old real number scalar whatsoever. If those are given, this implies that scalar multiplication okay, I'm guessing all of you have had vectors, both of you have had vectors, and it's just like scalar multiplication of vectors. The scalar multiplication of A by the scalar C is another M by N matrix. So it's going to produce a matrix just like scalar multiplication of a vector produces a vector of the same dimension, okay? And this will be CA. But what CA is, and this is again just like with a vector, it's the entry CAIJ. So in other words, the C is multiplied by every entry in A. So every entry in A is multiplied by C. Just like with a scalar multiple of a vector, you multiply every component of that vector by that scalar C. Now, with that in mind, let's pick a very specific scalar C, -1. Okay? So let's multiply -1, or just minus, times A. And what do we have here? And by the way, that's the definition of scalar multiplication. This is the verbiage after that. So -A represents -1 times matrix A. Okay? Now, if A and B are of the same size, identically the same size, then A minus B is another way of writing A, matrix A, plus the opposite of B. Just like right up here. The opposite of A is -1 times A. So really, just like with signed numbers, when you're subtracting signed numbers, you add the opposite of the number. Same thing here when you're subtracting two matrices. They have to be the same size, of course. You add the negative of the second matrix. Okay? So with that in mind, let's do example 3. Now this is going to take some time and space. So I'm going to erase all those. And they're going to give us matrix A and B. Here's matrix A. 1, 2, 4. -3, 0, -1. 2, 1, 2. Matrix B. 2, 0, 0. 1, -4, 3. -1, 3, 2. Okay. Given those two matrices, we're asked to do a few different things. The first of these is a scalar multiplication. 3A. The 3A is going to be 3 times every element in A. So that would be 3, 6, 12, ugly 6, okay? -9, 0, -3, 6, 3, 6. All right. That's the A part. The B part is, what is -B? Well, that is negating every element in B. That would be a -2, 0, 0, because the negative of 0 is still 0. -1, 4, -3, 1, -3, -2. Okay, so there's -B. Okay. I didn't stop and make sure I got. Yeah. Yeah. Now the C part says to do 3A minus B, which is just adding 3A to -B. So just adding element by element. 3 minus 2 is 1. 6 plus 0 is 6. 12 plus 0 is 12. -9, -1 is -10. 0 and 4 is 4. -3, -3 is -6. 6 and 1 is 7. 0. 3 minus 3 is 0. And sort of got lost there. There we go. 4. 6 minus 2 is 4. I thought someone was at the door. They weren't. Okay. 1, 6, 12, negative 10, 4, negative 6, and 7, 0, 4. So there was example 3. They took a bit more space to do. I was looking at theirs, but still we needed the whole page. Now, the next thing we're going to do is do matrix multiplication. Okay. We've done matrix addition and scalar multiplication, and then by defining a -1 times scalar multiplication of -1 times a matrix, then define that to be matrix subtraction. Like I said, we still haven't talked about matrix multiplication. We did scalar multiplication by a matrix, but not matrix multiplication by a matrix. And there is a way to do that. They first give an example. And I don't know how much of this to do. I don't want to do all the gory detail of it, but at least set it up for you. Okay? And this is getting close to some real applications that people do use matrix operations for. Let's say you are a college running a football stadium, or a local municipality running a football stadium. But it's not one of these super big ones, it's just a regular, and it has 3 concession areas located in the south, north, and west stands. Your top selling items in these concession stands concession areas are peanuts, hot dogs, and soda. You can tell this was written by someone not from the Southeast. Okay, most of the time we don't call them soda. I guess some people do, but of course most of the time we just call them Colts, but that's not good either. Soft drinks, something, but they call them sodas. Okay. All right. Now, sales for one day are given in the first matrix below, and the prices in dollars of the 3 items are given in the second matrix. So in the first matrix, we're going to have 3 rows. The first row stands for the south stands. Okay. The second row for the north stands. And the third row for the west stands. Okay. Now, those are the 3 rows. Your 3 columns represent peanuts, hot dogs, and sodas. Okay? Peanuts, hot dogs, and sodas. Now, this would be the number of these items that were sold at each stand. So at the south stand, they sold 120 units or bags, whatever it is, of peanuts, 250 hot dogs, and 305 sodas. Okay? On the north stands, they sold 207 peanuts, 140 hot dogs, sorry, my pen drags sometimes. I get lost going back and forth. 419 sodas. I don't want to make any super big deal about this, but of course the north stands would be facing the southern sun, so if this was a hot fall day, I can see why 419 sodas would be sold in the north stands. Okay, the west stands, which I can hardly read my writing there, must be much smaller. 29 units of peanuts, 120 hot dogs, and 190 sodas. Okay, now this column matrix or column vector represents the selling price. You got $2 for your hot dogs, $3 for your got that backwards. $2 for the peanuts. Okay, sorry, I knew I dropped a line in my vision there. This is the peanuts. I'll put PM for peanuts. $3 for the hot dogs and $2.75 for the sodas. Okay. Now, there are several things you can do with this, and one thing would be this. What is the revenue, the gross revenue that you got at each of the stands? Okay? What you would do then is multiply south stand, 120 bags of peanut for $2 a bag, 250 hot dogs at $3 a hot dog, and 305 sodas at $2.75 each. So that would give you the revenue from the south stands. North stands, 207 peanuts times $2 a bag. 140 hot dogs times $3 a hot dog, plus 419 sodas sold for $2.75 per soda. And then the west stand, same thing, 29 by 2 plus 120 by 3 plus 190 by 275. And that would give you the total amount of revenue you had at each of those things. So notice what you did. First row by first column here, entry by entry by entry. Second row by first column here, entry by entry by entry. Third row by first column here, entry by entry by entry. Adding those together, and that gives us, and I'm just going to use their numbers so I won't have to do the multiplication, 1828.75 was the total revenue from the $1986.25 for the north stands, and a mere $940.50 for the smaller west stands. Okay? Now, notice what the product is. Look at what we've done here. We've taken a 3 by 3 matrix, multiplied it by a 3 by 1 matrix, and our answer was a 3 by 1 matrix. Okay? Now, they all aren't going to be this symmetric, but let me point out one thing. Since you had 3 things you were selling, and you had to have those 3 prices here, the number of columns in the first matrix must equal the number of rows in the second matrix. And sure enough, these have to be the same. Once you strike those, then you have a 3 by 1 left, and that is your answer here. That's in sizes, okay? And indeed, that's always going to be the case. Now, the definition of matrix multiplication, as if this wasn't, in a sense, somewhat complicated itself, wait till you see the definition. And it's fine, it's absolutely true, but just looking at this doesn't make it make necessarily that much sense. Here's a definition of matrix addition. If A is this matrix Aij is an M by N matrix, okay, and B is this matrix. Now, we're going to use, well, they use same subscripts. I really don't care for it too much. Ij is a N by P matrix. Okay, N by P matrix. Then the product matrix this is matrix multiplication. AB is, and you can multiply M by N by M by P as long as these two innermost dimensions are identical. And your result then is going to be an M by P matrix. Okay? And that matrix, AB, is going to have dimensions Cij. Now, I kind of don't like the same indices being used, though it's okay. But here's what Cij is. It's going to be the summation k equal 1 to n, where n is that inner dimension, the last of the first and the first of the last, okay, that inner dimension of Aik from the first one times Bkj from the second one, okay, and that would be, let's just start the k's from 1 and going up to n. So AI1 B1J plus AI2 plus B2J plus AI3 plus B3J plus ... all the way up to and including AI in the last entry, B in J. I can't write. I can't read. Okay. Now don't tell me I forgot to turn on my pause button. I can't remember now. I just did. It's 12:41. I don't know. I was paying so much attention to the book, I may have missed that. Okay? And that is a definition of matrix multiplication. here's how I'm going to show you, and this to me works just as well, okay? And you can follow what they do in the book, and that's fine. But let me leave this with you because we only have a few minutes left, how I like to look at this. Here we're looking for a product AB. A is the matrix, -1, 3, 4, -2, 5, 0. Yeah. Okay. And I always like to note what the size of that is. That is a 3 by 2 matrix. 3 rows, 2 columns. And here's matrix B. And matrix B is -3, 2, -4, 1. Okay? That happens to be a 2 by 2 matrix. So the first question I ask myself, can you even multiply these two? Yes, you can, because those two inner dimensions are the same. Same number of columns of A as rows in B. That's a requirement. Okay? Now, what is the size of your product? Let's just say we're multiplying these two together. The product is going to be what's left, 3 by 2. So here's what I do. I put in, whoops, you have 2 columns. And 3 rows. There's your 3 by 2 matrix. Now, and that's your product AB. Okay? Now, the first entry is a 1, 1 entry. To get your 1, 1 entry, you take the first row of A by the first column of B, multiply and add. That would be -1 times -3 is +3, plus 3 times -4 is -12. +3 minus 12 is -9. Okay? The next entry here is the 1, 2 entry. So you take the first row of A again, but this time by the second column of B, 1, 2. That would be -2 plus 3 is 1. Okay? The next entry here is the 2, 1 entry of AB. That's the second row of A times the first column of B, 2, 1. That would be -12 plus 8 would be -4. Okay? Then the 2, 2 entry here, second row by second column, that will be 8 minus 2 is 6. The 3, 1 entry here will be third row of this one by the first column of that one, first row of A, multiplied and added to the the first column of B. -15 plus 0 would be -15. Your 3, 2 entry here will be third row of A, second column of B, and that would be 10. Okay. That is how you multiply these matrices. If you can multiply them. The size has to be right. Sizes have to be right. And sure enough, that's what they got. -9, 1, -4, 6, -15, 10. Okay? And then at the bottom of the page, they do show that same thing I did. Why don't they do that at the top? I don't know. Now, before we leave this page, even though I know we're out of time, there is Arthur Cayley is mentioned here. He's a very good potential paper topic. He was a lawyer by profession, but he began groundbreaking work on matrices. It mentions 2 other, and these happen to be American. He was British mathematician Benjamin Peirce and Charles Peirce, his son, and among the 3 of them, they came up with matrix algebra. There's a little QR code there that probably gives you more information. Remember, this may give you ideas for your paper, but this can't be your source. You need to get your source elsewhere. Okay. We will begin next time with a rehash of what we just did, top of page 44, and then we will move on from there. Let me give you homework exercises here. I think you can do 1 or 3. They're both at calcchat.com. And you can do the operations of matrices 5 through 9, odds 5 through 9. They're at calcchat.com. I think you can do 11 and or 13. And you can start working on finding products of two matrices 15 through, well, as many as you want to do. We'll continue that next time, so if you get stuck on some of those, hold off and we'll do more later. All right, that's going to finish up. Sorry, I only got a little over an hour recorded. I hope I didn't leave my recording off too long, but I did have a couple breaks when I had to go get something and a student needed something too, so maybe we're just about right.